This is the IEEE Computer Society Distinguished Lecturer webinar series brought to you by the Distinguished Visitors Program. The Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interactions, and to the membership through webinars by respected professionals. We have distinguished visitors around the world who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program. Welcome to our Distinguished Lecturer webinar series. My name is Kerry Cosby, and I'm the Chapters Manager at the IEEE Computer Society. I oversee our more than 600 professional and student chapters around the world and manage our Distinguished Visitors Program. I'd like to take care of some housekeeping tasks before we get going. You can ask your questions in the Q&A panel. Dr. Petty will answer as many questions as he can following the presentation. When you're writing your questions, if it relates to a particular slide, please do your best to reference that slide. The webinar is being recorded, and the recording will be made available after the webinar. The Computer Society provides various resources for you to expand your knowledge and learn more about the computer graphics field. Stay on top of the latest trends and best practices by exploring Computer Society Digital Library, which has published nearly 5,000 articles and papers related to this research in this year alone. The massive inventory features the journal IEEE Transactions on Visualization and Computer Graphics, which published over 400 peer-reviewed papers. Furthermore, you can connect and grow with other professionals via our technical community on visualization and graphics. More information will be shared after the webinar. You can learn more about this also on computer.org. In today's webinar, Dr. John Petty will present mesh shaders and the history of computer graphics. The webinar looks at how mesh shaders offer a full compute mode for shading, which includes transformations, tessellations, texture, and baked-in rendering. Dr. Petty looks at all aspects of mesh shaders and how they can support computing. This webinar is being brought to you in partnership with the Distinguished Visitors Program and the Computer Society Baltimore Section Chapter. I'd like to introduce our speaker. Dr. John Petty is a recognized pioneer in the graphics industry, president of John Petty Research, and named one of the most influential analysts in the world. He lectures at numerous conferences and universities on topics pertaining to graphics technology and the emerging trends of digital media technology. Former president of SIGGRAPH Pioneers, he serves on the advisory boards of several conferences, organizations, and companies, and contributes articles to numerous publications. In 2015, he was given the Lifetime Achievement Award for the CAAD Society. Dr. Petty has published hundreds of papers to date and authored and contributed to 11 books. His most recent, Augmented Reality, Where We All Live, Dr. Petty is a former ACM distinguished speaker. His latest book is Ray Tracing, A Tool for All. Dr. Petty, I'd like to pass the floor to you.
Well, thank you. Good morning or afternoon, wherever you are. It's early morning for us. Just to give you a quick hello, who we are. And already I failed how to advance the slides. There we go. So he mentioned I'm from John Petty Research, and we do technical marketing research on things of computer graphics. That's our primary focus. We do quarterly reports and annual reports and biweekly reports, and we advise almost all of the companies in the hardware and software sizes of the computer graphics industry, as well as the financial community. They're very interested in what's going on in computer graphics. So get right to it. The agenda is that we'll do a walkthrough of the pipeline. This really is going to be a pipeline discussion, and we'll use that concept and that model for explaining the evolution of how we got to mesh shaders. And it's a long trail. It took a while to get here. It sounds very easy once we get there, but it wasn't. So I want to start off with a little video here. This is a video made by NVIDIA, and the reason we're showing it is because NVIDIA was they introduced mesh shading, and they also introduced a couple of other features of mesh shading, which we'll go into a little bit more detail. So watch this video. Now, when you do watch it, it's only about 1.5 minutes long. Look in the lower left-hand corner of the screen, and what you'll see there is a set of rolling numbers. And what those numbers represent is how many vertices are being processed instantaneously and in real time. And I apologize for the music. We tried to figure out how to get rid of it. Can't do it. So I won't be able to talk to you while it's playing. And let's see if this works. There we go. Bam. So I think it's pretty fantastic. I remember the first time I saw that video, I actually didn't believe it. I thought it was some kind of trick, or I thought it was pre-made and they had just speeded it up to show it. But that was a capture of a real-time meshing success. So how did we get here, and why did we get here? Well, we have Moore's law to thank, basically. We have this very large-scale integration capability that has grown and grown and grown over the past three decades or more, actually 4 decades. And the idea of how a GPU works is not new or novel in any way. In fact, it was, I think, first developed back in the late 60s, early 70s. So NVIDIA didn't invent the GPU per se, but what NVIDIA did was they were the first company to integrate transform and lighting processors into a graphics controller. And when they did that, they invented basically what we now know as a GPU. And they also coined the word GPU, so they're inseparable now. You can't say GPU and not think of NVIDIA maybe. But nonetheless, it pushed us into the era of a fully integrated device that had transform and lighting in it, which is critical to computer graphics. And they were doing it at consumer prices because they were building these things for games. So those two items together, the integration and the consumer level pricing, really propelled the industry forward. and we've never been the same since. So as I mentioned, we always had transform and lighting. You have to have it. You can't make computer graphics work without it. But we would use external coprocessors, either a floating point processor, sometimes it was a DSP, sometimes with dedicated little state machines. So when the integrated processor came along, we now had the ability to do transform and lighting within the chip, and that not only speeded things up and lowered costs, but it also gave us a new programming model to work with, because we now could deal with one API and address one device instead of a whole bunch of devices. So it sped things up that way as well. Excuse me. When we first started with transform and lighting in the GPU, it was kind of a fixed function. Now, it wasn't hardware fixed function, it was a software fixed function, but nonetheless, so it could only do that thing. And so in 2000, short period of time after the introduction of GPU, Microsoft, with the assistance of NVIDIA and ATI, introduced a programmable vertex shader. And that was a big deal also. So that got us started towards the path of using these little processors that are in the GPU in a more robust way. And so that gave us, that led us into the geometry pipeline, which begins, as I mentioned, with vertex shaders. We basically have to transform the virtual space of a 3D model, which is arbitrary. And we have to transform that into the visual space of what's on the screen. And that sounds kind of straightforward and easy, but it really isn't, because it's a three-dimensional matrix problem and everything moves or can move. And so therefore you have to have control of everything. And that's the tricky part. So here we go. I can't see that. Anyway, it should be vertex data and primary data. I know how to make this bigger. There we go. So it's vertex data and primitive data goes in, and then we can tessellate it if we have that hardware or that capability. Then into the vertex shader, through a geometry shader, finally to the pixel shader, and out to the image itself. So this is the basic pipeline that still exists today, and did exist back, all the way to the 70s, but in less integrated form. The term shader, we have to thank, where'd that go? Stop. Sorry about that. Okay, now see if we can get George to sit still. Okay, so I guess not. I don't know how this is working or why it's doing this. Anyway, what that said was that we have George Lucas to thank for the term shaders. He actually came up with the idea that in order to make computer-generated film, which is what he wanted to do and a lot of other people did as well, we had to be able to color, to shade polygons, triangles, because they would be the basic construct, the basic primitive of any geometry shape that you can think of. And so he referred to it as shading, and that became a term that people could easily use to get a concept across to each other, and so they just applied it to everything. So now any processor that's in a GPU is referred to as a shader, regardless of what it's doing, whether it's shading, doing vertex or geometry or whatever. So we call them all shaders. And so we have vertex shaders, geometry, tessellation shaders, etc. So, but you should remember that shader is kind of a synonym for processor. So think of it that way if you have discomfort with the word shader. So this is, or that was, the famous Utah teapot. I am not in control here. Try this.
John, it looks like there are timed animations in here. That's possibly what's causing the problem.
There shouldn't be, but in any case, I guess it is. Anyway, so the geometry pipeline evolved But it took some time. We had to learn how to use these things, how to program them, how to make them behave the way we wanted to. And at 2007, we increased the pipeline to add this tessellation block. That was a very important thing. And tessellation is the concept of reducing the number of polygons as the image or the object, the object gets further away from you. Obviously, if you've got an object, let's say with 1,000 triangles in it and it's up close, you want those triangles to give you the refinement of the shape of the object. But as it moves into the distance away from you, you can't see them. So there's no reason to process them. So what tessellation does is it just basically throws them out. It collapses. It takes, two triangles that are together and makes them into one triangle, maybe a square or an oblong, and keeps doing that and keeps doing that as we move further away. 2006 was a big change for us because what we were doing is we were putting processors, again, integrated graphics were taking advantage of Moore's law, and we were putting more and more processors into the GPU, but the problem is we weren't utilizing them very efficiently. So we had processors that were being dedicated to do vertex work, and then we had processors that were being dedicated to do pixel processing, the actual shining of the pixels. But while one operation was going on, those other processors were just sitting idle, and so that was silly. We knew that. It was just a little more tricky to figure out how to get it to work. So in 2006 with DirectX 9, we got to what we called unified shaders. And the idea here was that we wouldn't label the shader as to whether it was vertex or graphics or any tessellation or anything else. We would just say, here is a shader, and let's use it for whatever job we need to do. And so if we need a whole bunch of vertex work done, then we can, allocate all the processors we can for that operation. And then when it's time to start creating the picture, we can now take those same processors and allocate them for rendering. And that was a big, big step. It wasn't an easy step because we had to relearn some programming stuff. The APIs had to change dramatically. There wasn't too much change in the hardware, except that we had to open up some registers to make them a little bit more accessible. But it had a dramatic effect on what we could do and how fast we could do things in computer graphics. Then in around 2016 or so, AMD came up with this idea of task shaders, and they also got called primitive shaders. This moved us even further towards a compute model and away from fixed functions. So we still had the pipeline concept because we did still have to, process things in a sequential manner, but we didn't have to have physical allocation of things, and that was really important. Primitive shaders, I might point out, are the heart and soul, if you will, of the PlayStation 5. That's making very big use of primitive shaders, and you can still do primitive shaders, by the way. So basically, all they do is they just say, look, a processor can be a domain shader or a vertex shader. And that's just a function of how you instruct it. So this becomes the precursor, if you will, to mesh shading. And so in 2018, NVIDIA presented a paper at SIGGRAPH on the concept of doing mesh shading. And this was something, we all knew this was coming and looking forward to it, but it wasn't, like I said, it just wasn't as easy to do as it is to say. But nonetheless, when it did break through, and NVIDIA gets full credit for this, the organization like Cronus, which makes Vulkan and OpenGL and so forth, adopted it, and Microsoft quickly adopted it also with DirectX 12. And so now we had mesh shaders. Excuse me. But the problem with mesh shaders is that they have certain restrictions. Which I'll get to in a second. So this is just showing you now what has happened to the pipeline. As you remember, we had 6 or 7, maybe 8 blocks there. Now we've squeezed it down kind of to 3 because the allocation of the processors no longer has to be specific. We can just say, look, there is a sea of processors, and there are thousands of processors in a GPU. So here they all are, and let's use them for whatever needs to be done, whatever the workload is that we need to get the process done there. So we leave this concept of marching in tandem, so to speak, soldiers marching along a linear pipeline, and get into the genuine capability of a GPU, which is that it's a similar instruction, multiple data, parallel processor. And that's its magic, and that's its power, is the fact that I mentioned we have thousands of them, literally thousands, of 32-bit floating point processors in a GPU. And we can now run them simultaneously, doing different tasks to get to a finished graphics image. However, as I mentioned, the meshes themselves, the mesh processing concept, was limited to 256 vertices. And that's okay, because NVIDIA came up with another great idea, which is called Meshlets. And you think of these as being supporting actors, so to speak. These are processes that can be run on these thousands of shaders that we have, and they can get down to the detail. And you recall in that video we just ran, I pointed your attention to the numbers in the lower left-hand corner. Those numbers were a result of the meshlets. That was showing you how all these little processors can get into the job and make a contribution. And so the concept's easy to understand. You have a traditional triangle count, and you can see how many vertices there. So three triangles, one count per vertice. But now the meshlets gives you a broader view of the world, so to speak. And so now you more than double your ability to do processing of vertices and other coordinate information. So that led us to the amplification shader, which is really nothing more than a display list, if you will. It's a job listing. It says here's the work that we're going to do, and it sends down the tasks to get processed. So that's what it looks like symbolically. Keeping the pipeline concept in mind, is that the amplification shader sets up the job, sends threads to the mesh shaders. The mesh shaders then process, do what they have to do. We run in and out, pull in texture maps when they're needed, can do tessellation operations if needed, and then start the output, and then run a pixel shader. So it's very, very much simplified. The programming is a little bit more complicated, as you might imagine, because you have to keep track of a lot of different things now. And that puts a little bit of burden on the content creators. The whole thing about building stuff is that you have to be able to test it and prove it, and you also want to be able to brag about it. And so benchmarks are the way we do that. And there's a company called FutureMark, or they were called FutureMark. Now it's Underwriter Labs. They were acquired by Underwriter Labs. But before they were acquired, FutureMark had been the producer of all kinds of graphics benchmarks going back 20-some years. And they've created a benchmark for meshing. And I think I have a little demo here of it, yeah. So what you see here is the white lines represent the view. That's what you would see, say, on your screen, from your screen point of view. And what's going on here is these are all the little meshlets and mesh shaders going on, are doing their job, so to speak. Because we have thousands of shaders, processors in the GPU, each one of those little dots can get a processor for a few seconds or milliseconds even, to do the job. And so it produces intense complexity and detail very, very quickly. So what this is a still from that previous video. And what it's showing is the little red dots there that you can see, I hope you can see, are the mesh shaders doing their job. And when they finish, the yellow thing that you see, the shapes and so forth, is what they produce as they're doing their processing. And you notice it's all well lit and it's got shadows and, and reflections and so forth. And that's very important because that's the basis of realism. So we tested this in our labs, and other people have as well, got similar results. And with mesh shading off and using a modern GPU from NVIDIA or AMD, we could get 66 frames a second, which is fine. You know, there's nothing wrong with that. Turning mesh shading on, and we got, 700% improvement. Now, no one's going to run a 551 frame per second image. That's just crazy. But what it is telling us is that we now have this enormous processing capability available to us so that we now can put really big, complex models into the GPU and get results out, not just in our lifetime, but within a few milliseconds, 30 milliseconds, for example, or even 16. And so that's where the excitement happens, because now the complexity of the model goes up almost exponentially, but we still keep the same frame rates. So we're getting to the end here. This is a longer video I'm going to show you, and this is, my grandmother used to say the proof of the pudding is in the eating. This is the eating. I've been telling you about the pudding. Here it comes. Now, watch this and watch it carefully. It's about 5 minutes, maybe a bit more. Epic, who makes Unreal game engine and Fortnite and a few other things, built this demo, and they explain it, and I'm going to let them explain it because they do a very nice job of it. But they built this demo. It reminded me the first time I saw this of Tomb Raider. I don't know if any of you have ever played that game or looked at it, but it has a lot of the qualities of that in terms of the caverns and the ancient old buildings like this and so forth. So it's just a really enjoyable video. I've seen it probably 100 times now.
Hello, I'm Brian Karras, Technical Director of Graphics here at Epic Games.
Hi, I'm Jerome Plateau, Art Director of the Special Project.
A few years ago, we got together as a team and brainstormed where we thought we could push forward the state-of-the-art in real-time graphics. There were two key areas that stood out. The first, dynamic global illumination. Beautiful bounce lighting instantaneously.
I don't have to be constrained to do a game where the world has to be static, and I'm able to iterate a lot faster.
And we call this new system Lumen. And we're about to show you what it is capable of. But first, there was another area that we thought we could push forward. Truly virtualized geometry. The artist wouldn't have to be concerned over poly counts, draw calls, or memory. Could directly use film quality assets and bring them straight into the engine.
And that's a big deal for artists. I just want to be able to import my ZBrush model, my photogrammetry scan, my CAD data, without wasting any time optimizing, creating LODs, or even lowering the quality to make it hit frame rate.
In the end, that's what it's all about. Art that just works. And we call this new technology Nanite. Here is the future of Unreal Engine running live on a PlayStation 5.
Awesome. Let's take a look at it.
This has to be the right way.
Before we continue, let's stop a moment and take a look at some of the key features of this demo. Much of what you see was built with Quixel Megascan assets, but instead of using the game versions, we used the cinematic versions, which would typically only be used in film. There are around 1 million triangles each, and thanks to virtual texturing, they all use 8K textures as well. Nanite can render an insane number of triangles very quickly. There are over 1 billion triangles of source geometry in each frame that Nanite crunches down losslessly to around 20 million drawn triangles. What does that many triangles look like? This isn't noise. These are the triangles, each a different color. Most are so small that they look like noise. Nanite achieves detail down to the pixel,
which means triangles are often the size of pixels. This amount of geometric detail requires shadows to be pixel accurate as well, and nanite can do that too. Speaking of lighting, all of the lighting in this demo is completely dynamic, with the power of Lumen that even includes multi-bounce global illumination. No light maps, no baking here. Without GI, all of that beautiful lighting is gone. With Lumen enabled, we can move the light and the bounce changes instantly. Okay, let's keep going.
Is it running in real time? By the way, it's not fake.
We've made some great additions to our audio system as well. Convolution reverb allows us to measure reverberation characteristics of real spaces, like actual caves that we sampled, and reproduce them in virtual spaces. Sound field rendering allows us to record and play back spatialized audio. All of this adds up to a more immersive experience. This swarm of bats was created with our Niagara effects system. Particles in Niagara can now talk to one another and understand their environment like never before.
And that's done procedurally, by the way.
We've also added a ton of new functionality to run fluid simulations like you see in the water below. The demo runs on our chaos physics system. Here we are using it to accurately simulate the rigid bodies of the falling rocks and the cloth of her scarf. Now that the environment is so complex, we've needed to greatly improve our animation systems to adapt. We've added predictive foot placement and motion warping, which dynamically modifies IK and body position to look more natural. For the character to more realistically interact with the environment, we've added the ability to trigger seamless contextual animation events, like her hand on the door.
Looks promising.
Dynamic GI is amazing, not just for speeding up iteration, but also for its impact on gameplay.
Nice.
Any light source can move while still having beautiful bounce lighting. Dynamic illumination means specular as well, which you can see on all the metal surfaces. You can even see the Niagara-powered bugs reacting to the light. Lumen not only reacts to moving light sources, but also changes in geometry. Remember we mentioned high poly assets? This statue was imported directly from ZBrush and is more than 33 million triangles. No baking of normal maps, no authored LODs.
And they replicate that 100 times.
And we can do more than a single statue. There are nearly 500 of that exact statue at the same detail level placed in this room, for a total of over 16 billion triangles from statues alone. Over this entire demo, there are hundreds of billions of triangles. So with Nanite, you have limitless geometry, and with Lumen, you have fully dynamic lighting and global illumination, all running on a PlayStation 5.
There's not much time left.
And this doesn't need to be constrained to small rooms. It can stretch all the way to the horizon.
The portal, it's open. Don't fail me now. Time to see what's next.
You want to see it again? So if that doesn't drive home the point about what you can do with mesh shaders, nothing will. So the thing about it to keep in mind is that it doesn't come for free. There is programming involved, serious programming. But the results are just incredible, absolutely amazing, and you'll be seeing this in terms of games and things probably mid 2022, maybe a little bit later. It just takes a lot of time to build a game up. I mentioned that there's a white paper on this. If anybody's interested in it, you can have that. These slides are also going to be online, so that you can look at them later if you choose to. There's my email address. I answer all email. And then take a look at this for a little while. Here's some resources that you can use to get more information on mesh shading. Excuse me, NVIDIA and AMD have a bunch of great white papers. Microsoft, with Mesh Shader Spec there with Microsoft, they have a fantastic white paper. I mean, if you really want to dig into this and understand how to program and what the results will be, I highly recommend that. Cronus has similar papers on their webpage. So you've got 4 really good sources there, and you're going to get a 5th one pretty soon, which is going to be Intel, because they're introducing a GPU as well, and they're also going to be able to do mesh shading. So five sources, Microsoft, Cronus, AMD, Intel, and NVIDIA. And this information's there, and it's free, and they'll even help you if you ask them to. So that's it for me. Now, I guess it's time for Q&A.
All right, thanks a lot. Man, the graphics on those were incredible. We've got some questions that have come in, and if anybody else has any other questions, feel free to put yours into the Q&A box. Dr. Petty will answer them as they come in. The first question that we've got in here is, in all of your slides, this was early on, by the way, in all of your slides, you don't mention the SGI contributions at all, OpenGL. The SGI team moving to NVIDIA, etc. What are your thoughts on this?
SGI gets a lot of credit for helping this industry exist. It goes back to 1981. The guy that started SGI, Jim Clark, for his PhD thesis, he's at University of Utah, he introduced the concept of using VLSI again, of building a geometry processor. So this was a standalone processor that was dedicated to just doing geometry, the thing that we eventually put inside to make a GPU. And on the basis of that, he then started Silicon Graphics Corporation, SGI. And SGI really propelled the CG industry, the computer graphics industry. They built some of the world's greatest workstations. Even by today's standards, those workstations are still amazing. They were also expensive, which was a bit of a problem. But the team that came to, the people who came to SGI were really the foundation of the hardware CG industry, and the software too, for that matter, because a lot of the software that we take for granted came from companies that Silicon Graphics had acquired and expanded. The company kind of got out of sync with the industry as we moved into the era of the PC and the what's called commercial off-the-shelf COTS processors, like the Intel 386, for example. The cost to build a computing device dropped dramatically. And SGI had their own processor at the time, built on MIPS, and it was a good processor, nothing wrong with it, but they never could get the volume to get the cost down, and so they were kind of running against a tide that they couldn't. Like Dell, for example, and HP later started building workstations using Intel processors instead of custom processors, and it totally upset the entire workstation market. And in the process of while that was going on, NVIDIA got started and introduced the integrated GPU. And then there was a dispute between NVIDIA and Silicon Graphics, and they had a lawsuit and so forth. Anyway, they settled it and amicably, and a whole team of people left SGI and went to NVIDIA. So a lot of the foundation work that created the computer graphics industry moved to NVIDIA, and that helped them do some of the great things that they've done over the years, such as mesh shaders and unified shaders, things of that nature. So we used to make a joke about the wandering tribe of computer graphics engineers. So I don't know if that's a full answer to the question, but if it isn't, ask it again and I'll try again.
All right, I think that works. The next person was just interested in what the name of the game was in that video that you had shown. Oh,
well, it's not a game yet. It was a demo prototype. Nanite is the only thing that it's referred to as. Looking at the games that are available from Sony for the PS5, it's difficult to pick which one it might be. As I mentioned, it reminded me of Tomb Raider, and so I'd say keep your eye out for a Tomb Raider-like game, or maybe even a new Tomb Raider for that matter, on the PS5. But it'll be an exclusive to Sony for the PS5, and I think it'll be pretty easy to spot once it shows up.
All right, thanks. The next person asks, when will we get to the point where the animation is indistinguishable to a human from real-life video? Where can we go once we get beyond that point?
Well, you could start by watching the movie Gravity, because I think it's something like 50% of the acting that's in Gravity is animation. And it's a controversial subject in Hollywood, especially with regard to Academy Awards, is can an actor or actress, or say it differently, should an actor or actress be awarded an Academy Award if the majority of their acting is done by CG? And as you can imagine, when you do a space story like Gravity was, you can't take actors into outer space and throw them around and have them do crazy things and so forth. So you had to do it. So it's a really funny story. I made a talk at a conference. If I just remember how long ago this was, it was at least 15 years ago. And I predicted at that conference that by 2020, character animation would replace human acting, and that the characters would never go on strike, and they'd never take a coffee break, and they'd look and be great and so forth. So my prediction of 2020 was off by about 4 years, because Gravity came out and proved that we could do that. all the special effects that you see in movies, that's all CG. And if you look and you see people tumbling over through the air or falling from the sky, and they always have that kind of landing that they make, that's all CG. So there was another great demo that Epic did of this gangster kind of guy smoking a cigarette. He's real badass, and he flips a cigarette and he jumps off a building and he lands just perfectly. Total CG. But it is so good that you suspend disbelief almost immediately and buy into it. And that's the magic, is you get into the story. You stop looking at it and you start experiencing it. That's the trick. And so we're there, in my opinion.
Amazing. A lot of people are asking where they can find that video. Is there some sort of a link or something that they can get to get that?
Should be on Epic's website. If you can't find it, I mean, I have it, and I'd be happy to. I mean, it's big; it's a gigabyte, I think. But anyway, I can put it in a Dropbox or something for you. If you can't find it, just send me a note, and I'll make it available to you.
Okay, that works. How difficult is it to get started with Unreal Engine? They ask.
Well, if you asked Epic, they'd say, that's easy. Just sign here. You have to understand C, obviously, C++, and you have to have a good grounding in computer graphics, understanding what it means to take geometry and reshape it and then reposition it in a different world, get the transformations right. And you also have to be able to weave in the supplemental stuff, such as physics and audio. And then you have to deal with the lighting to make sure that you're casting shadows in the right way and getting reflections correctly and so forth. So there's a lot to learn. There's a lot to do in it. But Epic and their competitor Unity have done a really good job, I think, in their user interface, in that they make it, boy, as easy as I think it can possibly be made for a person to get their hands on the engine. You don't have to drill down into the microcode of the game engine to work it. I mean, the UI will pull you out far enough that you can give it straightforward instructions, like move light from here to there, make light brighter, things of that nature. A lot of sliders and knobs involved. So I'd say if you're comfortable programming, if you consider yourself a programmer, and if you think you have a reasonable understanding of computer graphics, jump in. The easiest way to find out how hard something is go do it, and expect to fail. In fact, if you don't fail, something's wrong, and just keep at it. But I encourage you to go for it. If you've got an idea for a story or something, and you want to build a game or maybe an animation or something, the use of game engines now has gotten to be so extensive. Many movies are using game engines for the development of the movie. Almost every advertisement you see for a car has a game engine behind it.
It's amazing. This next person says that you mentioned that you need programming for this. Does that programming include memory management as well?
Mm-hmm. Yeah. You have to be aware of the models that you're building and the support data that you use for those models, such as texture maps, for example. So you have to keep all that in mind and know just how much memory you have, and also how you can access that memory. There's multiple layers of memory in terms of size and speed, starting out with L1 caching, going all the way out to the mass storage. And one of the things that happened in the PlayStation 5, for example, which is really interesting to me, hopefully it'll be interesting to you, is Sony, with the cooperation of AMD, did a really good weave of SSD to the memory in the main RAM and the GPU's memory. And it's so seamless and so fast that game developers had difficulty with it at first, because they were used to using what are called cutscenes. And a cutscene is a little video. So as you transition through a game, you get to a certain point, and it's time to load some new maps to get to the next stage of the story. And so you put a cutscene in, and it plays some video, and it sets up the concept for the gamer to get ready to go do what he or she has to do for the next stuff. Well, with the tightly coupled SSDs, there's no cutscenes needed anymore, and it's because the maps will load incredibly fast, and as a result, the game developers, had to relearn. They had to learn some new tricks, and it actually slowed down game development time a little bit, but it dramatically speeds up the game itself.
Okay. So your cat there is just a graphic, right? That's not a real cat.
That's an animation. That's not a real cat.
So this next question, I think they're probably just going to have to get in touch with you offline, but they say that they are interested in creating 25 unique stories on ancient wisdom. They want to know how you can help.
Well, I'd say the first thing is, do you have a sponsor? So you need a grant or somebody who's going to help fund and pay for the equipment and time and the things to do things. In terms of tools, I can point you at the various companies out there that are making tools. Most of the companies that make software tools for computer graphics have educational discounts, and they're happy to grow the environment, if you will. There's all kinds of classes and things that you can take online that are free to learn how to use these tools. NVIDIA has, and so does AMD, have sponsorship programs and intern programs. So there's a lot of resources out there to help you get started.
Okay, great. This question just came in. The person says, I joined a little late and with a bad internet, so you probably already addressed this in the presentation. Their question is, apart from knowing some programming, where can one start ideally?
That's a good question, actually. Well, without knowing where this particular person is, it's a little difficult to say. My personal preference is to do it, to just jump in and try and do something. I'd say if you have some comfort in programming, then build something. Go create a 3D model. Assuming that you have, go create a 3D model in some application. There's lots of them that you can do. There's free ones that you can download from the web, and just build something in 3D. And you connect lines, make a 3D square, put a roof on it, maybe something like that, and then start coloring it, fill it in, do flat shading and so forth. But basically, just jump in and try it. Okay,
great. Gives everybody just a couple of more seconds to add some questions here if they want to. Now, one of the things that I have noticed on YouTube is they've started putting these kind of graphics things for people to watch. Is that some way that somebody can kind of get an idea, start out in doing this, to create their own little things like these videos on YouTube?
Yeah. In fact, YouTube's a good vehicle because it's kind of like where the rubber meets the road type thing. If you can produce an animation, let's say, and again, there's free animation tools available. If you can produce an animation and you want to get a sense if it's any good or not, other than showing it to your friends and family, post it to YouTube and see what happens. See if anybody reacts to it, see if they like it. And I should say that there's a couple of YouTube channels, and I don't know them off the top of my head, I'm sorry. I've visited them from time to time, but there's a couple channels where there's enormous collection of animation videos that and amateur videos as well with live actors have made. And I'd say do a little searching for that and see if you can find that and look at those libraries. And that'll tell you what the level of quality is that viewers are expecting now. And so that'll be like your bar, right? You say, okay, that's what they're used to seeing, so I got to do that well or better if I'm going to get any hits on this.
All right. Well, I'd say this has been Oh, sorry. Go ahead.
I was just going to say, be prepared to fail. You know, if you don't fail, you don't learn. You know, and you shouldn't be embarrassed by it either. You know, put it up there and if people say, that's crap, I don't want to see that. Okay, take it down, try again. You know, how did you learn to drive? You know, you hit things and then you finally figured out, oh, don't hit things.
I'm trying to teach my son to drive, and hopefully he's not going to hit that many things. So
You hit curbs. I hit curbs a lot when I learned how to drive.
Well, I'd like to thank you very much for your presentation today, Dr. Petty. It was wonderful. I'd also like to thank all of the people here who've attended with us. You guys have been great. The questions you've given are great. Our next Distinguished Lecturer Webinar Series webinar will be Transparent, Trustworthy, and Privacy Preserving Supply Chain. That'll be given by Dr. Salil Kanhare tonight or today, wherever you are. For me, it'll be tonight, midnight. So if anybody wants to stay up and join me for that one. And then our Build Your Career webinar series will have its next presentation on Persuasive Conversations, Why Low Impact Words Don't Work by Elsa Velasco-Paul, and that'll be on November 18th. Registration is now open, and we will be sending you guys a link to this in the future and future events with the recording of this webinar. So again, Dr. Petty, thank you very much. This has been a great presentation. We really enjoyed it.
Thank you. Appreciate you attending. Bye-bye now.